if I wanted to describe a wave, let's say sine wave or cosine wave, and let's say this is P, Q, so P is equal to the cosine of Q. What is the period? And symbol for period is T. Period is how long it takes for a wave to be completed. So what's the period? Now in class, usually somebody will say 2 pi. And then I follow up with, what's the wavelength? And then there's some hesitation, and then somebody says 2 pi, and I go, what? For this graph here, is 2 pi the period or the wavelength? And it really depends upon what Q is, whether it's a period or the wavelength. Now, I do not recall, I remember doing this stuff in math class, I guess pre-cal, but I don't recall ever having to deal with the fact that whether it's a period or wavelength, which one matters, it comes down that we were given the appropriate one for whatever the question was asking, but now we can't do that. We now have to take into account the fact that waves do not just move with time, do not change with time. It's not like I have an amplitude changing with time like in harmonic motion. I have a wave that is actually traveling through space and time. So how do we express that? Well, I have two things to keep in mind here. There is something known as the angular frequency, and there is something known as the wave number. Yes, we're using K yet one more time. So as I produce a wave, if I'm producing a wave here on a coiled spring or something like that, I move it back and forth, the time it takes me to go from there and back is the period. So that's the actual time. So let's just think about, all I'm doing is just creating a wave. We're going to come back to those numbers and those things in just a second. So if I have something, so I start here, other side and back. So my amplitude, will just say y is equal to whatever my initial amplitude is, or this is how far I am from 0. So if that's 0 right there and I start here and move back and forth, that's my amplitude. Y is just where I happen to be at that moment, times cosine of omega t. So all I'm doing is just moving back and forth. I know that cosine repeats itself when that is equal to 2 pi. If you think about the unit circle, we're at 0 here, 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, and then 2 pi radians. So when I get back to here, I'm repeating myself. So when omega t is equal to 2 pi, that's when it repeats itself. Well, if it's repeating itself at that point, that's my period. So this is omega capital T is equal to 2 pi. And so my period is equal to 2 pi over omega. If I am looking at changes in position, so I have a wave that is basically sort of fixed in time at the moment. If I'm starting here, this is the point at which the wave starts to repeat itself. So this is equal to, let's just say x is equal to some amplitude, whatever that distance right there is. There's my amplitude, times the cosine of kx. We probably should not have the same variable both places there. So why don't we make this y? And it repeats itself when kx is equal to 2 pi. So since this is the length it takes to repeat itself, this is my wavelength. So this is k lambda is equal to 2 pi. So my wavelength is 2 pi over k. So I have two situations here. I have something oscillating back and forth, basically in the same, over the same location. So I got a spot right there that it's oscillating over. And then I also have a wave that extends through space. So to take both of them into account, we can express the wave as equal to some amplitude times the cosine, or sine if you like, kx minus omega t. And so this takes both of them into account. The speed of a wave like this is simple enough. I know that speed is equal to distance over time. And if the distance is the wavelength and the time is the period, we have this. This is if you then translate that to frequency, you'd have V equals lambda F, which is something you should have seen in the first semester course. But lambda is equal to 2 pi over k, and period is 2 pi over omega, but it's 1 over period, so it's omega over 2 pi. So a speed of a wave that is described by this is equal to omega over k, the angular frequency divided by the wave number. And that will come into play in just a moment. We're going to use two of Maxwell's equations. So I have E dot dl equals negative change in flux, magnetic flux with respect to time. And P dot dl equals mu naught I plus mu naught epsilon naught d phi E dt. Since we're talking about electromagnetic wave here, there's no traditional current, so that part just goes away. And I'm going to describe my electric field as maximum electric field strength times cosine of kx minus omega t. My magnetic field, some maximum value for the magnetic field, times the cosine of kx minus omega t. They work in hand, they'll have the same wave number, the same angular frequency. So if I imagine that I have some electric field that's oscillating back and forth, it's moving with time, that's my electric field. I have a magnetic field that actually is perpendicular to it, and just sort of go with me on that. That's my attempt at a three-dimensional drawing. So this is going in that direction, this is going in that direction. So what I'm going to do is start out with taking a small little square right here. I'm doing an Amperian loop. So if I look at that, the distance right here, that it is an Amperian loop, so it has some physical dimension, some distance h there, and this distance right here will be dx. My magnetic field at that point, my electric field, let's take the point where my electric field is that value right there, and then right next to it, that value right there, when they're infinitesimally close to each other. So this would be E, and this would be E plus dE. There's some small, this is infinitesimally small distance here, and some infinitesimally small change in electric field. My magnetic field is coming out of the page at the moment. So that is my magnetic field coming out. We assume that this distance is so small that there's no appreciable change in the magnetic field here. And so I am going to employ Faraday's law. And I'm going to start at this point, and I'm going to do my line integral going around. So the way I want to go is going to be the way that basically produces a right-hand rule in the same direction as the magnetic field. So I'm going to call this 1, 2, 3, and 4. So Ampere's law says that E dot delta L1 plus E dot delta L dot delta L2 plus E3 dot delta L3 plus E4 delta L4 equals, that's basically going around E dot dl all along, negative d phi m dt. E1 dot L1 is in that direction right there. There's my delta L1, and that is perpendicular to my electric field, so that's 0. Same with 3. 2, I'm going in that direction, so this is E plus dE times that length right there, which is h, plus 0 plus, and then this right here, my DL is going, I'm trying to get back to the start, so DL is going that way, but E is going that way, so it's negative EH is equal to, well, the magnetic flux is B times A. So this is negative ddt of my area, which is H dx, times B. Now let's make sure that's on screen there. So summarizing, we have E plus dE times H minus EH equals negative ddt of HB dx. Rearrange the order of the letters a little bit, and dx goes together. If we distribute, we have EH plus HDE minus EH is equal to, well, H and dx don't change with time, so this becomes negative H dx times dB dt. My EH's cancel. And then so we have H dE equals negative H dx. And then dB dt, remember that B is equal to some maximum value times the cosine of kx minus omega t. So dB dt becomes Bm. Derivative with respect to time, this is the part we're affecting, so we got a negative omega. And then derivative of cosine is negative sine kx minus omega t. So we end up with, well, I have H on both sides, so H goes away. And I'm going to bring the dx over here, so I have dE dx is equal to my maximum value of the magnetic field times omega. I got the one minus sign left over, so I can get rid of two of them. Sine of kx minus omega t. Well, if you remember, E is equal to some maximum value of the electric field times the cosine of kx minus omega t. When I do the derivative with respect to x, then I get a k out front, so I have EMK times negative sine kx minus omega t is equal to negative Bm omega sine kx minus omega t. Well, my minus signs cancel. Sine kx minus omega t we can get rid of. And so, or we could say the coefficient, if this is always true, the coefficients are always the same. So EMK is equal to B sub m omega. We'd already looked at the fact that the speed of the wave is equal to omega over k. So omega over k, which is equal to the speed, so bring that over here, is equal to the magnitude of the electric field, the amplitude of the electric field over the amplitude of the magnetic field. We are halfway there. Next step, going back to our original drawing, I now am going to do an Amperian loop along the magnetic field lines. So if you imagine that it is sort of my electric field and my magnetic field like that, I'm now going to look at it from this direction, sort of tilted up like that. So while this is still here, so I'm going to basically draw my box here, length h. This is dx. My magnetic field, B plus dB. And my electric field is going into the board, or into the page. Because again, it was like this, and I'm tilted up that way, so I'm looking that way at it. So let's bring that over here. D, B plus dB, dx. This distance here is h. Now, the way I want to carry through my loop here is I want to loop it so that with the right-hand rule, I'm pointing in the direction of the electric field. Electric field is going into the page, and so I'm going to go around that way. So I'm going to start here, and this is 1, 2, 3, and 4. I know that the sum of B dot dl is equal to mu naught epsilon sub naught d phi e dt. For 1, I'm going in the same direction as my magnetic field, so this is BH. Here, the dot product is 0 because my magnetic field is up and dl is that way. Here, I'm going in the opposite direction, so this is B plus dB times H, and then negative because they're in opposite directions, and then 4 plus 0 is equal to mu naught epsilon sub naught times d area times the electric field dt. So this is BH minus B dB is equal to mu naught epsilon sub naught. My area is constant, so that is h dx. And then change in E with respect to time. Again, E equals E sub m cosine kx minus omega t. And then B will be bm cosine kx minus omega t times dE dt. Those cancel out. I'm left with negative B dB. Negative B. Yeah. No. H dB. So I'm left with negative H dB is equal to mu naught epsilon sub naught H dx times negative omega em negative sine kx minus omega t. This negative here comes from that negative right there, and this negative here comes from the fact that we're doing a derivative of cosine. They will cancel out. Matter of fact, h cancels out. And so I have negative dB dx, bringing that over, is equal to mu naught epsilon sub naught omega em sine of that stuff. dB dx right here, so this is negative k b sub m negative sine kx minus omega t is equal to mu sub naught epsilon sub naught omega e sub m sine kx minus omega t. The minus signs cancel out. We can get rid of the sign, and I'm left with k sub bm equals mu naught epsilon sub naught omega e sub n. I know that the speed is omega over k. So let's get omega. So that comes over here, and all that goes to the other side. So that's going to be equal to b sub m over mu sub naught epsilon sub naught e sub m. And let's make sure that is actually on screen there. There we go. So from the first equation that we did, the first round, when we used Faraday-Lentz's law, we had the speed is equal to amplitude of the electric field over the amplitude of the magnetic field. The second time we did it, we had it's equal to the magnitude of the magnetic field over the magnitude of the electric field, and then we had these extra terms here. If I multiply both sides by em, so basically bring that up and that down, we have em squared over bm squared is equal to 1 over mu sub naught epsilon sub naught. If I take the square root of both sides, I get the square root of 1 over mu sub naught epsilon sub naught. And that is just E sub m over B sub m, which is just the speed. This is the speed of an electromagnetic wave. Traditionally, the symbol used for that speed is the letter c, it's the lowercase c. So Maxwell went through the calculations, and we can do some crude calculations right here. U sub naught is in SI units, 4 pi times 10 to the negative 7th. Epsilon sub naught is 8.85 times 10 to the negative 12th. So if I multiply those together, so 4 enter pi, do 180 and convert, times, and then E7 negative times. So that is mu sub naught, 8.85, E12 negative times, and then take the reciprocal and the square root, and I end up with 2.9986330 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 8th, and that would be meters per second. Maxwell at this point sees that and says, I do not know if light is an electromagnetic wave, but it seems like too much of a coincidence. He speculates. He doesn't have enough arrogance to just go out and say it, but he speculates that light is an electromagnetic wave. And he nailed it. Light is. This had matched because the calculated value matched so closely with the experimental value for the speed of light. And this is the point in which, for the first couple of years I taught at Forsyth Tech, I then went straight into relativity because it goes so nicely. However, we do take a break here in order to do AC circuits as a request from a student who ended up being an engineer, in which he had at least some background to it. I do want to point out here, here's sort of the question that I will not answer at this point, but physicists looked at it and said, that's great, but something is wrong. And so this is the 1870s. So this is the prediction for an electromagnetic wave. Hertz then goes and actually is the first one to find experimental evidence for the electromagnetic waves, where he detects electromagnetic waves in 1887. However, I think it's around 1870 Maxwell does this. For the next 35 years or so, some physicists said, this is great, but there is a mistake here. They didn't know what it was. A guy named Lorentz jumped through hoops to try to explain why this is what he derived, even though that there was a mistake. And it's actually not resolved until Einstein comes along, 1905. Incredible year for Einstein, and that will be picked up later. But the question to you is, why would anyone think that there's a mistake here? And I guess the hint that I generally give in class is, how fast are you moving right now?